Alright, let's not waste any time. Let's go ahead and jump right in. And I finally have a sand timer again, so we're going to keep track of that. Alright, 6.6 homework. Let's look at question number 1. First one says, plot all 4 points in the same complex plane. Okay, we've got 3 plus 7i, 5 minus 3i, negative 7 plus 7i, and 3i. Okay, first one, 3 plus 7i. So the real axis is what we do, the real component. This is the real component. And this is the imaginary component. So you graph the imaginary component, the imaginary axis, real component, real axis, x, y, combine those, good to go. So 3 plus 7i, 1, 2, 3. And let's see, 3 and 7 should be right about there. So this is the I-axis, this is the real axis. Yep. And let's see, 5 minus 3i, we would do, let's see, 5 minus 3i, that'd be 5 to the right, and then negative 3. So you go down 3, 5 to the right, down 3. And it goes 1 right there. So that's that. Let's see. Negative 7 plus 7i, we go 7 to the left, and then we go up 7. Because this is like, if you want to think about it this way, you can think this is the x coordinate, this is the y coordinate. But it's really that this is the real coordinate, this is the imaginary coordinate. So we have real and imaginary. So we do negative 7, and then 7i. I think it's about right there, if I'm approximating correctly. I think it's it, yeah. And then finally, we have, what was the last point? Just 3i. Okay, 3i, there's no real point, it's all imaginary. So go, it's just y, so we'll just graph it right on the y-axis. So this is 3i right there. Great. So then that's problem number 1. That's as simple as it is. And it looks like our answers are pretty good. This is pretty good. Did I get the second one right? Yeah, I got the second one right. Cool. Great. All right, problem number 2. We have find the polar form of the complex number where 0 is less than or equal to theta, which is less than 2 pi. Now you might notice that all these problems look a lot less trashy than the last set. I mean, it actually looks neat and organized. Maybe this will help us figure it out easier. Okay, so to figure out this problem, we've got negative 9i. Let's see, it's currently in the a plus bi form, that rectangular form, a plus bi. And you can kind of notice that a equals 0 and bi equals negative 9. Or you can say just b equals negative 9. Okay, I suppose the easiest way to do this is to start by graphing it. If you don't have any sort of formula jumping out to you, a graph is a great way to go. And I think that'll really show you what's going on here. Let's see. So we'll graph 1, 2, 3, 4, 5, 6, 7, 8, 9. Because 0 plus a negative 9i, if you were to graph that in the plane, this would be down here, negative 9i. You can kind of guess, you can kind of just see what this is. 0 plus negative 9i. Well, if we had a line, that was going all the way down there, that would be, let's see, the radius. The radius would be 9. And the angle, what would the angle be? Well, that's between 1 pi and 2 pi. It'd be 2 halves pi and 4 halves pi. It'd be 3 halves pi. This is 3 pi over 2. Unit circling can confirm that if you're at all concerned about that number. So this would be, so if our formula then for this is a plus bi equals r times the cosine of theta plus I times the sine of theta. Well, we can just plug literally that in and then just replace the theta and r with 3 halves pi and 9. So let's go ahead and do that. So we have, let's see, r is 9, so negative 9i equals 9 times the cosine of 3 pi over 2 plus I times the sine of 3 pi over 2, and we're done. Cool. Next problem. Find the polar form of the complex number where the argument satisfies 0 is less than or equal to theta, which is less than 2 pi. So somewhere between 0 and 2 pi. And if you have to choose between 0 and 2 pi, you choose 0. Now remember, again, argument means angle. The angle is between those two. Okay, so you can see what this looks like. You can notice that in this one, a and b, a is 3 root 2, and b is 3 times the square root of 2. So they're both the same thing. So if you were to graph it, you would have something looks like this, something just looks just like that. So if you can kind of imagine what that triangle would be, so this length is the same thing as that length. This is 3 root 2. This is 3 root 2. You might be able to guess what kind of triangle this is. This is a 45, 45, 90 triangle. So this is 45 degrees. So we'd say, immediately we know, okay, the angle is 45 degrees. We'll plug in 45 degrees for our answer. Oh, 45 degrees, excuse me, that's not, it's pi over 4 is what that is, 45 degrees. I'm just uncovering the answer all willy-nilly, but that's what it is. 45 degrees is pi over 4. That's what is preferred, pi over 4. Now we just need to figure out how big that radius. And we know that for a 45, 45, 90, let's make sure we stay in the right problem. For a 45, 45, 90 triangle, 45, 45, 90 triangle, we've got 1, 1, and square root 2. That's our kind of formula here. So we can multiply, let's say this would be 3 times square root of 2, 3 times square root of 2. That would give us, 3 times, so this would be, on this radius, or what we'd multiply it by. If we want to multiply this by x, it'd be x, and then x squared root of 2, if you want to think about it that way. So this would be, the radius would equal 3 root 2 times that root 2. So this is equals 3 times, let's see, root 2 times root 2 is just 2, which equals 6. So our answer is 6. I hope that wasn't too confusing. Okay. Number 4. It says determine whether the following statement is true or false and justify your answer. The polar form of a complex number is unique. Okay, so we're saying we've got a complex number, and the polar form of that complex number, the polar form, so if we've got the complex number a plus bi, then the polar form of that number is going to be the same number all the time. So we have, let's say that the polar form, or the trigonometric form, is r times the cosine of theta plus I times the sine of theta. So it says there's only, if there's only one of these, there's only one complex number, there's one of those, then this means there's only one of these. Now, is that true? Well, remember what we said about roots, and how, the side that I made when I was talking about roots, about how we could add 2 pi to any angle and it'll still be the same angle, Yeah, we can do that. So if I add 2 pi to theta, it'll still be a coterminal angle, so it'll compute out to be the same number. So it still works out to be the same thing, even though the angle changes. It's kind of like I can spin around a bajillion times, and I'll still get to the same position. I can keep adding 2 pi to theta. So this could be theta up here, or I could make it theta plus 2 pi. Or I could make this one theta plus 2 pi. I could keep doing that. So in other words, the modulus of a complex number is unique. So the modulus, the radius that we have, that's going to be unique. But the argument that theta, the angle that we have, that can change because we can add 2 pi to it or subtract 2 pi from it if we rather. So the answer to this one would then be B. Yeah. All right, number 5. Number 5. Write the complex number in standard form, a plus bi. It says 13 times the cosine of 60 degrees minus I times the sine of 60 degrees. Okay, so we need to find this in the form a plus bi. Well, I think this one might actually be a little bit simpler than the problems from beforehand, as far as like it's the reasoning needed to figure it out. Supposedly, perhaps not. We know that a. So we have from the lesson above, we found out that a equals r times the cosine of theta, and b equals r times I times the sine of theta. And if you didn't know that, if that was something that you'd forgotten from the lesson, you didn't memorize that rule, it's fine. You can just draw a triangle and you'll see the same thing. If you try to graph something, and you want to find where it is, you can make a little triangle and you can say, oh well, yeah, the radius if I want to find a or bi, I would just use trigonometry and I would get these same values because this is the radius, this is theta. You can use sine, cosine, tangent, and you'll find out the same thing. Okay, so all we have to do is plug and chug here. So we've got the radius is 13. Our radius is 13. And theta equals 60. Cool. So we just gotta plug it in and we'll get our answer. Let's see, A then would be our radius, 13, times the cosine of 60, or 60 degrees. And then BI would be the radius times, or excuse me, not the radius, just 13. It's 13. 13i times the sine of 60 degrees. Okay, now if you have your unit circle, or if you've memorized it, which I hope you have, you'll probably recognize that the 60 degrees is right up here. And so the sine would be the square root of 3 over 2. The cosine is 1/2. So we'll go ahead and plug this in. So the cosine this would be 13 times 1/2. This would be 13i times the square root of 3 over 2. And so that gives us for A equals 13 over 2. And for B, oh my goodness, I'm kind of all over the place right now. Just for a second, just give me a second here. Okay, I got so many papers, I don't know what to do with them all. BI equals 13 times the square root of 3 over 2. And all that times I. Great. And that would be our answer. So we'll just write 13 over 2 plus 13 root 3 over 2i. And that's our answer. Cool. Number 6. Number 6 asks us to write the complex number in standard form, a plus bi. So same procedure. We have a equals r times the cosine of theta, and b equals, bi equals ri sine theta. Let's see. Our radius equals, in this case, would be the first number, that's root 10. And then our, let me move pages here. Got so many notes. Yes, so our radius would be root 10. And then our theta would be, what is theta? Theta is negative pi over 6. Okay, so if we want to find the square root of 10, so a would be the square root of 10 times the cosine of negative pi over 6. And remember the negative pi over 6, we're going back on the unit circle, so it's subtracting 1 pi over 6. So the same thing as 11 pi over 6. So cosine of that would be the same x value as if we were going above on the unit circle. So that is going to be root 3 over 2. So this gives us a equals root 10 times root 3 over 2. And that gives us, let's see, that'd be the square root of 30 over 2. And that seems about right. And then we do the same thing for I, or sorry, for BI. So BI equals the square root of 10, times I times the sine of negative pi over 6. And let's see, negative pi over 6, the sine of that would be negative 1/2. I don't know if you can actually read this from this. I think this might be really too small for you because my window is really small on your screen. So I don't know if you can actually read the circle. This might be a completely unhelpful showing it to you. I'll find that out in post. So this would be root 10 times I. Oh yeah, and the sine, of course, is negative 1/2. Same thing, just negative. Same thing as pi over 6, but negative. That gives us negative root 10 over 2. Okay, so our final answer is root 30 over 2 minus root 10 over 2i. Oh, sorry, there's an I over here. I almost forgot the I. Oh, I did forget the I. Okay, That is number 6. Let's move on to number 7. Find the product of z1 and z2. Leave the answer in polar form. So now we're moving on to multiplication in the notes, or in the lesson, the video from before. So we have z1 and z2. Remember, in order to find the final radius, all we have to do to find the final radius, the radius, is just r1 times r2, and theta is just theta 1 plus theta 2. And we just plug it back in, and we'll get z1 times z2 equals radius 1 times radius 2 times the cosine of theta 1 plus theta 2. Because this is the standard form. I'm just replacing theta and radius with radius 1, radius 2, theta 1 plus theta 2. But this is just the standard form, plus I times the sine of theta 1 plus theta 2. Standard form augmented with changing theta and radius with radius 1, radius 2, theta 1 plus theta 2. Okay, radius 1, radius 2 equals, so 6, that'd be radius 1 is 6, radius 2 is 3. Let's see, theta 1 is 151, theta 2 is 114. Radius 1 times radius 2 would be 18, so we get 18 times the cosine, not the cosine, the cosine, cosine of 151 plus 114, that'd be 265. Oh man, I am really embarrassed myself. I don't know if it was, I think it was pre-calculus. I mean, it might have been college algebra, but I just get numbers way off. But I'm pretty sure that one's right. I'm adding those two numbers. Plus I times the sine of 265 degrees. And that is all there is to it. But that's our answer right there. I could put that in the answer box right down here, but you know what it is. And yeah, that's it. Okay. So then the next one, number 8. Let's move on. Find the polar form of the quotient. And you know the quotient is well, that's dividing, so we're dividing. Quotient means divide. And we're going to do the exact same thing, except we're just going to take the two radiuses and divide them, and then the thetas and subtract them. So radius equals radius 1 over radius 2, and theta equals theta 1 minus theta 2. So we had radius. So if the final number is radius times the cosine of theta plus I times the sine of theta, then it'll also be radius 1 divided by radius 2 times the cosine of theta 1 minus theta 2 plus I times the sine of theta 1 minus theta 2. All right. So radius 1 divided by radius 2, that's 20 divided by 4. 5 is 4. Equals 4. Theta 1 minus theta 2, that's 140 minus 110. This is 30 degrees. This is 1, this is 2, this is radius 1, radius 2, theta 1, theta 2. Just in case there's any confusion. And we'll plug it in. So this gives us 4 times the cosine of, let's see, that's 30 degrees, plus I times the sine of 30 degrees. And that's the answer. That's it. All right. That's a page turn for it. A page turn for me. We're still good on time. This is great. We're going to cruise right through this lesson. Find the product z1 and z2 and quotient of z1 divided by z2 in 2 ways. Using the polar form for z1 and z2, and B, using the standard form for z1 and z2. Okay, so we're going to use both the standard form, or the rectangular form as I've called it, and we're going to do the same thing with the polar form. We're going to do both those operations. Okay, so it gives us the standard form, the rectangular form, a plus bi. Just in case there's any confusion, this is standard. Okay, now it wants us to find. Oh, I guess the first thing it wants us to do is to figure it out using polar form. I guess we can do that. Sure, let's do that. So we start by just using our normal conversion. We'll say this is 12 minus 8i. So this is, oh yeah, we were 12 minus 8i, so we're going to convert to polar form. 12 minus 8i. So this would be, oh, let's make sure we make a graph. Just kind of graph it. 1, 2, 3, 4, 5, 6, 7, 8, 12, and then 1, 2, 3, 4, 5, 6, 7, 8. I think that's a little bit overshot, but you know, I can see the idea. Okay, so we've got this, and we are trying to find this. And if just in case you have any confusion how to get the angles, this would be, so the radius, so a squared plus b squared equals the radius squared. And so this will give us the square root of a squared plus b squared equals the radius. We don't include the I because the I is more just like a denoter in this sense. The way we graph it, it becomes more of like, oh, we're denoting the fact that it's on the I-axis, if you want to think about it that way. So we don't have to take the square root of I squared. We're fine there. We're fine here. So we can just say a squared plus b squared equals r squared, or a squared, the square root of a squared plus b squared equals r. We don't have to include I anywhere in this. Okay, so this gives us 12. This gives us 100, the square root of 144 plus 64. That's an 8. I would have said 6, but I wrote an 8. Equals r, the square root of all that. So that gives us the square roots of 110. No, 210 equals the radius for the first one. The radius, the first one, is the square root of 210. I believe, no, that's not 210. That's 208. Excuse me. So that's square root of 208. And yeah, and it looks like we're gonna be using a lot of decimals, so I'll just give a decimal for this one. So we'll find, just in case I had this wrong, so we'll do the square root of 144 plus 64. Oh man, if I add, I'll be so embarrassed if I added that wrong. That's 14.422. So the radius 1 equals 14.422. And yeah, and then the radius of the second one, we'll follow this. I'll just quickly do the radius of the second one as well, just to quickly get it through. So the radius of the second one is, let's see, well, our second number is 1 plus 1i. So that gives us 1, and then for a, so a equals 1, b equals 1. So we get the square root of 1 squared plus 1 squared equals r. And we have, that's just 2, square root of 2 equals r. And square root of 2 is 1.414. 1.414 equals r. Now I have a bad habit of not always rounding when I should. Did I round the last? Yeah, I rounded the last one correctly. Okay. Alright, now the second thing we're going to want to do is figure out the angle. So we found out the radiuses, or radii. I also have a tendency to say radii, or radiuses instead of radii. Now we need to find the theta. We need to find the argument of this problem. And there's a couple ways to do it. You could use, considering that we're dealing with a triangle here, and you could say, well, this is 12, and this is -8. We said this is 12, this is -8i. You could use trigonometry and just, whatever you're going to do, you're going to use trigonometry. You use sine, cosine, tangent, especially because you know the hypotenuse now. But the easiest thing, and I think the most reliable thing, especially because we're using, we're kind of estimating what the hypotenuse is. We don't have the hypotenuse down to like 100% precision, because we rounded it to 3 decimal places. The most accurate way, and I'd argue even the fastest way, is just to use tangent. And so here's the rule here. If we want to find theta, the tangent of theta equals b over a. And so if we want to find theta, we find the inverse tangent. So theta equals the inverse tangent of b over a. Now you might be concerned, a little bit about domain, because remember how we said it before, there's domain issues, but for tangent we'll be all right for this. Tangent is totally fine for what we're doing. The domain is not a worry for us right now. Even though you normally do, you want to make sure you're cautious of RY stepping outside of the domain of the appropriate inverse tangents, inverse sines, inverse cosines. That way, if you get like some sort of unreal answer in your calculator, you know why, because it's probably outside the domain. Anyway, all that said, we're just going to plug these numbers in. We literally just have to plug the numbers in, and we'll have the domain. So we've got, we won't have the domain, we'll have theta. So for the first one, for theta 1, that'll equal the inverse tangent of, let's see, b. B in our case is -8, and a is 12. So we'll say -8 over 12, And then for theta 2, we will put, well, that's just 1 and 1, right? That's just 1 and 1. Or b is 1, a is 1. So we can just write 1 and 1 for those. Okay, so that's just the inverse tangents of 1 and 1. Now be careful, which is also just 1. Be careful, make sure you read the instructions, that's important. It says that we're typing in angle measures in degrees, so we're going to make sure we're in degree mode. And we've got to make sure all our angles are between 0 and 360. So we're going to be cognizant of those two things. If we get a negative angle or like 400 degrees or something like that, we're going to have to modify, find a coterminal angle by adding or subtracting 360 degrees to make sure we're in the right place. Without further ado, let's go ahead and let's just enter these numbers in. So we've got, let's just pull the calculator out. You can see I've already done this once. Let's see, inverse tangents of -8 divided by 12. Not probably the first time because I got B and A mixed up. Don't want to do that. So that gives us -33.6.690. So this equals, not an O, it's a 0. I have a weird thing where I don't like saying O because it's not an O, it's a 0. It's a proper right 0. Anyway, but this is a negative number. We don't want negative numbers. We've got to make sure it's between 0 and 360. That's what the instructions say. So we'll add 360 degrees to it to get our number, 326. So we'll do 326 points, let's say 309. That rounds up to 310. Okay, and let's see, for theta 2, we have an inverse tangent of just 1. So inverse tangent of 1, and that gives us 45. Again, if you're not getting the numbers that I'm getting, if you're getting something weird that's really like really small numbers, then make sure you are in degree mode. If you're in radian mode, you'll probably get really, really small numbers, like fractions of a number, that sort of thing. It'd be like 0.5 or Anyway, so this is 45 degrees. This equals 45 degrees. Degrees. Great. All right. So those are our thetas. Theta 1, theta 2. Theta 1 and theta 2. And we're going to just plug these numbers in. And we can just move from here. Okay, so now we've gotten this, we can write, that's from last time. I made a mistake from last time, and now I had to redo this take. So, but we are now on the right track now, and you can see that I kind of erased the answers. But you can see I'm being totally honest, so these are the right answers. So 14.422 times the cosine of 326.3. Yep. You put in the radius, and then you put in the thetas where the thetas go, plus I times the sine of 326.331. There's a 1 there. And then 1.414, that's exactly what we have for radius 2, times the cosine of which should be 45 and 45. Good deal. So let's move on. So now it says, which choice shows the correct intermediate step when trying to find the product of the polar form? Well, remember, when you're trying to find the product, our radius becomes, or maybe more accurately, if you got a programmer's mind, you've got radius 1 times radius 2, and that becomes the radius. And then theta 1 plus theta 2 becomes the theta that you plug in for the answer. So radius 1 times radius 2, we got 14.422 times 14.422 times 1.414, and that gives us 20.392 for our radius. Oh wait, this is not even, I haven't even done the multiplication yet. So yeah, so we'd write 14.422 times 1.414. That becomes the radius part, and it looks like all of these have done that, and they've all done it, except I suppose if you want to really think about it, z1. If you're trying to multiply z1 and z2 together, uh, if you'd multiply the it doesn't matter. Never mind. What really matters is the second part. So we have to add that 45 degrees, or add the 326.31 and 45 degrees together. And it looks like, let's see, which ones do it? This one does not do it. They subtract. So that's not it. That's not it. The C, they take the 2 and they subtract. So that's not it. If we look at A takes 326.31 and adds it to 45. And it seems to have everything in the right order. So that's a good contender. And yeah, it looks like everything's pretty standard there. And then for D, we've got everything, but it's in reverse. We've got this is R2 and R1, and then theta 2 and theta 1. I mean, it'll get you the same answer. It'll be the same answer, but I guess what they're looking for is, I suppose, just doing exactly the right thing. This is radius 1 and radius 2. This is theta 1 and theta 2. Anyway, so that makes this one the right answer, and this one the incorrect answer. So A is right. Okay. So then it asks, which choice shows the intermediate step when finding the quotient z1 divided by z2 using the polar form? We have 14.422. Oh yeah, so it looks like if we're trying to divide those two, remember that radius 1 divided by radius 2 becomes the radius we put in, and then theta 1 minus theta 2 becomes the theta we put in. Okay, so we were looking for radius 1 divided by radius 2. That's 14.422 divided by 1.414, and then theta 1 minus theta 2, that's 326.31 minus 45, all that in degrees. Okay, so let's see, it looks like, once again, A is the one that actually has it down correctly. All the others seem to be different, so I think A is our answer there, because you've got 14.422 divided by 1.414, and then the degrees is 326.31 minus 45, right? The B asks, which choice shows the correct intermediate step when finding the product z1, z2 using the standard form? Now this one might be a little trickier because you haven't been doing it in a good long while. But let's look at the, let's remind ourselves of the problem. Here's the problem. Let's see. So you got z1 is 12 minus 8i, and z2 is 1 plus I. So z1 equals 12 minus 8i, and z2 equals 1 plus I. And so if we're going to multiply these two together, we can multiply them together just the same way we can multiply anything together, because they act like just normal numbers. It's great. It's perfect. So we just do 12 minus 8i. You might feel bad when you realize, oh, it's all we have to do is just to multiply them together. We just got a FOIL. Yeah, that's all we got to do. If you forgot, but this one's the easiest part of them all. So but that's all right. I mean, sometimes we forget. Sometimes it takes a while to remember. So 12 plus, let's see, first outers would be 12 outers would be plus 12i, and then inners would be minus 8i, and then last would be minus 8i squared. Okay, and then 12i minus 8i would be 4i. So that would be 4i. Okay, so it looks like which of these has that? That's C. C has that. So that gives us C's our answer. Cool. Which number should both z1 and z2 be multiplied by to complete the intermediate step when finding the quotient z1 over z2 using the standard form? Okay, so remember, this is something else that was a while ago when we remembered when we did this one, but it's in the same time period. Remember, when we try to divide by a complex number, what we want to do, what are things we really don't like. We don't like square roots in the denominator. That's one of the things we don't like generally. but we also really don't like I in the denominator. We need to do everything we can to get I out of the denominator. And how do we get I out of the denominator? We multiply by the conjugate. Yes, so we multiply by the complex conjugate of the denominator. So the conjugate of 1 plus I is 1 minus I. So we'll just put 1 minus I and 1 minus I, and we're good to go. And that's literally all we have to do. So using either Polish form or standard form, the product z1 times z2 simplifies to, oh, I gotta go back to what we wrote down before. Let's see. Oh wait, it tells us to put the form in standard form. Using either form. We have to figure out the answer and put the form in standard form. So if we're gonna put it in standard form, I might as well just finish up this over here. Finish up the standard form equation. I mean, both of them will get you to the same answer, but this is easier because it's already in standard form. So I'll just keep it in standard form. So this is, let's see, 12 plus 4i minus 8i squared. 8i squared is negative 1. So we get 12 plus 8 plus 4i. So that gives us 20 plus 4i. I think that's correct. Let me check my work so I don't give you the wrong answer. Yep, 20 plus 4i, and that is our answer. Okay. Using either polar form or standard form, the quotients of z1 divided by z2 simplifies to, now this down here would take a little bit longer. Actually, it wouldn't take too much longer. We could do either way, and either way would work just fine. Yeah, we could do either way, but I suppose let's go ahead and do the polar form just to show that it actually still works. So we'll take 14.422 and we'll divide that by 1.414, and we'll divide that by 1.414, and that gives us radius is 10.199. And let's see, so that gives us 10.199. So if we're trying to finish this up, this gives us 10.199 times the cosine. Let's see, the cosine of 326.31 minus 45. Let's see, 326.41.31 minus 45. Let's go ahead and store that. Store that as I don't know, let's say that, just store that as q, and then I'll take the cosine of q, which is 0.196, so that gives us 0.196, and then I'll add to that I times the sine of q, or sine of this number, sine of q. And if you're curious as to why I'm using q, it's just sort of have to type the numbers over and over again, just a little, 2 seconds faster. It's not all that important. And that gives us 0, negative 0. Let's make sure we're doing this clearly. I don't want to confuse you. It'd be I times negative 0.9805. Okay. And let's see, I'll take that and store that. I'll store that as E. And then let's see. And then I'll store this one. I'll store that. I'll store the x one as G. For I guess science is related to math. That's kind of what I'm doing here. And I should get out of alpha. There we go. Okay, so we're gonna multiply 10.199. Oh no! I should take this one. I should clear this. I'll take this and store that. The reason why I'm doing this, storing as letters, is because it makes it so that I'm multiplying an entire number by the entire number. I would otherwise be doing 10.199 times 0.196, which is still accurate, but it's just not. It's purely accurate. Okay, so let's do r times g, or the radius times the cosine. So radius times cosine, and I made cosine g. That gives us 2. That's 2. Cool. So we get 2 plus, let's see, and then we have the radius times, I really hope I'm not confusing you a whole ton with these letters. Again, I'm just using it so that I can multiply the entire number at once. The whole negative 0.9805804445557 without having to write out the whole thing. It stores that whole thing in the values of E and R, so I don't have to write the whole thing out. And that gives us negative 10. And so that's, I mean, it's a little bit of calculator error, but that's negative 10. And that's one of the reasons why I'm putting the whole number in there, so it's kind of easier to see the whole thing. And so we don't get any closer to an incorrect answer. So it's 10 plus negative 10i, or 2 minus 10i. And so we'll go ahead and plug that in. 2 minus 10i, and that will be our answer. And I think it's time for a break. Welcome back. Let's go to number 10. Using the Moore's theorem on indicating the power of the compound. So, to solve a problem like this, we're using the Moore's theorem, which is the same thing as power property. And remember, the power property, you don't have the tuition down in the pressure on the actual roof. It's E to the N R to the N times the cosine theta plus theta, we're setting it and then plus I times or maybe not imaginary, but implied 1. So we'll say the radius is 1. And how about theta? Well, theta is a lot easier to see. Theta is pi over 9. So we'll go ahead and use pi over 9 there. And let's see, so then the power of this would be z to the n equals 1 to the third power times the cosine of 3 times pi over 9 plus I times the sine of 3 times pi over 9. Okay, now 1 to the third power, that's just 1, and it'll cancel out, so we don't need to worry about that. But let's see, 3 times pi over 9, that reduces down to pi over 3. So we'll say this is pi over 3, and this is pi over 3. Okay, so we need to find the cosine of pi over 3. Let's see. The cosine of pi over 3 on our unit circle is, that's the first one, that's 30 degrees, sorry, the third one, that's 60 degrees, and so cosine is x value, so 1/2. So let's see, we have 1/2 plus, let's see, I times, let's see, the sine of pi over 3 is root 3 over 2, so we'll say root 3 over 2. And so that is literally our answer. So we have 1/2 plus root 3 over 2i, and that's our answer. Great. Let's move on to the next one. Let's look at number 11. Number 11 says use the trigonometric form and de Moivre's theorem to simplify this expression. 4 plus 4i to the third power. Okay, so we've got, let's see, we've got, let's see, 4 plus 4i to the third power. So it means we're going to convert this. If we're using de Moivre's theorem, we need to have everything in trigonometric form, or polar form, whichever term you prefer. So let's go ahead and convert that. So if I've got 4 plus 4i, if I think about that on a graph, that's right up here, 4i and 4. So that makes a really nice, neat triangle. In fact, it's It's the same size on both sides. It's a 4 and a 4, which means we've got a 45, 45 handed triangle. Very convenient. So we already know then that our theta is going to be 45 degrees because we've got 4 on the bottom and 4 for x and 4 for y, 4 for a and 4 for b. So we've got, let's see, 40. So theta is 45 degrees. And let's see, the hypotenuse, or the radius, is just the square root of 2 times the side. So this would be 4 times the square root of 2 is the radius. So we've got a radius of 4 times the square root of 2 and a theta of 45 degrees. And again, if you don't understand, use a trigonometric property anyone you'd like. You could use tangent, whatever you'd want to use, and that'll help you find that. Or you can just use the Pythagorean theorem, which is probably the most helpful, to be honest. So that'll get you 4 times the square root of 2. Okay, now let's go ahead and plug that in. So let's see. If I want to find that cubed, we'll go back to de Moivre's theorem, is z to the n power. So let's see, z cubed would be r to the n power. So it'd be 4 root 2 to the third power, and times the cosine of let's see, 3 times 45 degrees, and plus I times the sine of 3 times 45 degrees. All right, so let's see. Let's start with the 4 root 2 because that's probably of all the things here, that's probably the trickiest. Let's see, that gives us 4 cubed and root 2 cubed. 4 cubed is 4 squared is 16. 16 times 4 would be 64. So this would be 64 times, let's see, square root of 2. Square root of 2 times square root of 2 is 2. And then 2 times square root of 2 would be 2 times the square root of 2. So this gives us 128 times the square root of 2. And let's see. So we have, there's that, and then we have, let's see, the cosine of, so that's going to be all multiplied by all of that. Let's see, cosine is 3 times 45 degrees. 3 times 45 degrees, that would be 150 times 15, or 150 minus 15, which would be 135, I believe. Yeah, 135, so this would be 135. And you can think that's because 3 times 45, that's, if you can look at that graphically as well. 135 degrees, 135 degrees. So the cosine of 135 degrees, that would be right up here, right up on the top left of the unit circle. So cosine is negative square root 2 over 2, and sine is square root 2 over 2. So we've got negative square root 2 over 2 plus I times the sine of square root, no, not sine. Sine is square root 2 over 2. So sine is square root 2 over 2. Great. All right. This is a little bit messy, so let me just kind of rewrite this up here. This is 128 times root 2 times negative root 2 over 2 plus I times root 2 over 2. That's what I've written so far. Okay, now we're just going to go ahead and flush this out. We're going to finish this up. So 128 times the root 2 times the square root of 2, negative square root of 2 over 2. That'd be 128. The square root of 2's come together to equal 2. So it'd be negative 128 times 2 over 2 plus I times, let's see, 128 times 2 over 2. And if you're curious as to what I did, I just took 128 and multiplied that by, this is 128 times square root of 2 times square root of 2 over 2, and the negative version of all that. The square root of 2 times square root of 2, that's just 2. So that's kind of how I got the 2 there, if you're curious. Great, and then now, finally, we just reduce. So 2 over 2, that's just 1. So we can just kind of leave that out. That's negative 128 plus, let's see, 128 plus I times 128 times 1, 2 over 2 is just 1, so it's just times 1, so that means it's nothing. I could even write this instead of 128, I could write this as 128 I. And that will be our answer. So negative 128 plus 128 I is So that's our answer. Great. Let's go to the next one. Use de Moivre's theorem to find the indicated power of the complex number. 1 plus root 3 of I to the 9th power. This is where using de Moivre's theorem is much, much faster. You'll find this will be a ton faster than trying to do it out by hand. Or trying to do 1 plus root 3I by hand over and over and over again. In this case, doing it out by hand is much, much easier. If you convert it to trigonometric form instead of trying to just continue with the standard or rectangular form. Let's work this one out. So turning this into polar or trigonometric form so that we can use it. This would be, let's see. To do this, we would do 1 plus root 3 of I. So that means we go 1 across for A, and B is root 3. So that's a bad triangle. Let me just kind of make that clearer. This is 1. This is root 3. And we need to find the angle and the hypotenuse. Okay, so that's not a huge trouble. We can do this. We've got a theta, and if I want to find theta, the tangent of theta, so tangent of theta equals b over a, or root 3 over 1. So, or the opposite over the adjacent. So if I want to find theta, I will just find theta equals inverse tangent of root 3 over 1. Now root 3 over 1, that's just root 3. So I'm going to go ahead and pull up my calculator and solve that. So that'd be inverse tangent, second inverse tangent of roots, no, it's happening again, of root 3. And we will end that there. And so that would give us 60 degrees. Oh, well, yeah, of course. That is 60 degrees because the inverse tangent of, well, yeah, because if you divide the sine by cosine, you'll get root 3, square root 3 of 60 degrees. So 60 degrees, easy as that. I guess you could also see this is a 30, 60, 90 triangle, but I don't know, I just used a calculator because I did. So this is 60 degrees. So theta is 60 degrees. Let's find the radius. Radius is the same. The radius would be the square roots of 1 squared plus root 3 squared. So that gives us the radius equals the square roots of 1 plus 3, or square root of 4, which in our case, we don't really care about the positive value. We could go with the negative, but we'll say that this is 2, because the negative doesn't really make too much sense in what we're dealing with right here. We kind of know this is a positive value because it's 1. We know this is in the first quadrant. 1 plus root 3i. Okay. And usually when we do something like this, it's usually going to be in the first quadrant, if you ever are concerned. So usually the answer will always be, you should throw out the negative. If you need to throw something out, usually the negative is what you throw out. Anyway, I'm rambling. Let's finish this up. So using our formula from above, de Moivre's theorem, we have Zn. Let's make a little partition here so it's kind of clear. We have z to the 9th power would equal the radius to the 9th power, and the radius we found is 2 to the 9th power, times the cosine of, let's see, 9 times 60 degrees, 9 times 60 degrees, plus I times the sine of 9 times 60 degrees. Okay, and we just kind of compute this out. Let's find the 9th power of 2. So we get 2, 4, 8, 16, 32, 64. This is 1, 2, 3, 4, 5, 6, 7 would be 128. 8 would be 256. And 9 would be 512. Okay, so we've got z to the 9th equals, and I'm bleeding. I'm not bleeding over the next problem yet. Okay, so it equals 512 times the cosine of, let's see, what is 9 times 60 degrees? 9 times 6 is 54, so 540. 540 degrees plus I times the sine of 540 degrees. Okay. Now 540 degrees, that's above 360, and that goes beyond our inner circle. So we can go ahead and subtract 360 degrees to kind of get a better degree here. Or you can put this in your calculator as is, but I'm going to work it out by hand just in case you want to work it out by hand. That way you can get the true blue method. So let's see, 540 degrees minus 360. So 540 minus 360, that's 54 minus 36, which would be 18. No, yes. Yeah, it's 180. That's what yeah, okay. I was just, I don't know. There it is, 180. So we have 512 times the cosine of 180 degrees plus I times the sine of 180 degrees. Now, let's see. If we get 100 degrees, you can probably be pretty sure of what that is. That's -1. The cosine is -1. The sine is 0. So we will say this would be, this would be 512 times -1 plus, let's see, I times 0. And I times 0, that's just 0. So that's just 0. So it's just 512 times -1. So that equals -5, not -15, -512. -512. And it comes up to a nice neat answer there. So our answer is simply -512. And that's our answer. That's all we have. Great. All right, number 13. We've got this question. Use an algebraic method to find the cube roots of the complex number. Approximate exact solution values when appropriate. Okay, so they give us 13 times the cosine of pi plus I times the sine of pi. We need to find the cube roots of this number. So this is the first of the root problems that we have to do. And to do this, we can simply just remember the root formula. If you know the intuition, you can almost duplicate it on your own. But here it is if you don't have it yet. So let's start not even do cube root. Let's say the nth root of anything. The nth root of z is simply we've got the nth roots of the radius times the cosine of theta plus 2 pi k all over n plus I times the sine of theta plus 2 pi k over n. Okay, and then finally k equals 0, 1, 2, all the way up to n minus 1. Okay, so if we can just figure out the numbers, we can plug them in, and we can be good to go. Let's see. So let's see, our radius 13. Our theta is pi. And let's see the k. The n, and we're going to find the cube root, so our n is 3. Okay, so we'll just plug these in. And let's see. And to do this, it says that k is going to be 0, 1, 2, be 0, 1, 2, and let's see, to n minus 1, 3 minus 1, n minus 1 is 3 minus 1, which is 2. So we can stop there, 0, 1, and 2. So I'll make 3 versions of this problem, one for 0, one for 1, and one for 2. Let's start with the 0 problem. The 0 problem, we've got, let's see, the cubed roots of, the radius is 13, equals the cosine of, theta is pi, plus 2 pi times 0, all over 3, plus I times the sine of pi, plus 2 pi times 0, all over 3. And, oh, not 13, excuse me, not cube root of 13 equals, it's cube root of 13 times all that. Okay, that's the first one. Then we have the cube, if we do it with 1, be the cube root of 13 times the cosine of pi plus 2 pi times 1 over 3. Oh, excuse me. And then plus I times the sine of pi plus 2 pi times 1 over 3, and all that together. And finally, we'll do the third one. The third one is the cube root of 13 times the cosine of pi plus 2 pi times 2 over 3, and then I plus I times the sine of pi plus 2 pi times 2 over 3. There we go. All right, a lot of different things to write out, but the problems themselves actually aren't that difficult. We just got to jump through them. So let's see, pi plus 2 pi. I'll change color so it's clear that what kind of changes I'm making. Pi plus 2 pi times 0, this is just 0. So this is pi over 3, and this is 0, so that's pi over 3. Let's see, cosine of pi over 3. Cosine of pi over 3 is 1/2, and sine of pi over 3 is root 3 over 2. So we have this whole thing then. I can change colors again. This whole thing becomes 1/2, and this whole sine becomes root 3 over 2. So our final answer for that one is the cube root of 13 times, let's see, 1/2 plus root 3 over 2i. And we can actually leave that there. As far as the answer goes, that's acceptable. When we could work it out even further and multiply the cube root of 13 into it, but this is fine. This will do for our purposes. Okay, so that's one of the answers. Let's go to the next one. Let's see. Pi plus 2 pi times 1, that's 3 pi. That's 3 pi. And then this would be 3 pi. 3 pi divided by 3, that's just pi. So this becomes just pi, and this becomes just pi. So let's see, cosine of pi, that's -1. Sine of pi is 0. So all this becomes -1, and this becomes 0. So let's see, we've got the cube root of 13 times, let's see, that'd be -1 plus, let's see, I times 0 is just 0, so that's just 0. So this is just the same thing as saying -1, -1. So negative, which means that this equals negative cube root 13. And that's our answer for that one. So that's that answer. Okay. And then finally, on the right side, we have this one. Okay, pi plus 2 pi times 2. So that would be 2 pi times 2 is 4 pi. Plus another pi is 5 pi. This is 5 pi. And this would be 5 pi. So that gives us with 5/3 pi. Let's see, 5/3 pi is way down here in the unit circle. So that'll give us, cosine is 1/2. Sine is -3 over 2. So this gives us 1/2. And this is negative root 3 over 2. And all right, so we just plug it in, we'll be done. So root 3 of 13, or third root of 13, times 1/2 plus, or actually in this case minus, because it's a negative root 3 over 2. Negative root 3 over 2 times I would be minus root 3 over 2 I. And that's it. Those are our answers. Those are literally our answers. We plug those in, we'll be done. So I'm not going to rewrite all those, but this is answer number 2. This is answer number 1. And this over here is answer number 3. Those are our 3 answers. And there we go. Cool. All right, number 14. So he says, use an algebraic method to find the cube roots of the complex number. Approximate exact solution values when appropriate. Now it's important to realize in this one that that this one is not just an a plus bi form. It is an a plus bi form. We need to turn it into polar form and trigonometric form to make it work. Also, something to note, and I think this is weird, the answer it's looking for, although it says it's looking for, it says to type your answer in the form a plus bi, I think the answer it's actually looking for is in trigonometric form. So I think I might contact the publisher on this one and say, hey, there seems to be something wrong with it, because the answer they look for is not a plus bi, it's trig form or polar form. It's that. So you want to make sure that you do trigonometric form. Yeah. So we're gonna use it's going to be exact. So that means you need to find approximate. You need to write. Well, you need to, it's not exact. You need approximate exact solutions. So we're going to wind up with a lot of decimals. Anyway, all that through. Let's convert this to trigonometric form so that we can solve it. So the first step is we got 9 minus 12i. We got a and b. If you want to convert, if you want to find the radius is just the square root of a squared plus b squared. And theta equals the inverse tangent of b over a. And if that doesn't make any sense, if that doesn't make total sense, just draw a triangle and graph the point and see if you can work from there. You'll find the same values. And you'll actually end up doing the same process, very likely. So the radius is a squared plus b squared. So that means the radius, I'm going to move down here. The radius equals, let's see, 9, the square root of 9 squared, the square root of 9 squared plus a negative 12 squared. So that gives us equals the square root of 81 plus 144, which gives us the square roots of 225, which is the square root of 225 is 15. And because it's a long number, that's going to be, or because it's a line segment, we're just going to count it as positive. We know we're not using a negative value here. We're going to use the positive values. So this is 15. Okay, now how about for inverse tangent? Inverse tangent of b divided by a. Now, because we're going to go in trigonometric form, we want to make sure we're using radians. This is important. We'll use radians. Because otherwise you could end up in a hole. Because you're going to put this into an equation that requires radians. It's going to have pi in it, and so you want to make sure you're using radians. Anyway, all that said, we're going to make sure that I'm in radians, and I'm just going to plug this in. Hey, look at that. Keep it at 15. So we've got the inverse tangent of b, which is negative 12, divided by 9. And that gives us negative 0.927 radians. So theta, that's blue, I want purple. Theta equals negative 0.927 radians. Okay, so from here, it's pretty straightforward. You just plug and chug and see where you can go. So we have the equation is cube root of z equals, actually let's just do this, let's just write it out. Let's actually write out the whole thing. This is the cube root of z equals the cube root of the radius, and the radius, as we said, is 15. So the cube root of 15. And then times the cosine of, let's see, theta. Theta is negative 0.927. So negative 0.927 plus 2 pi times k all over n, which is 3, plus I times the sine of, because it's 3 because we're cube rooting it, just if you're lost there. I times the sine of negative 0.927 plus 2 pi k over 3. Great. Okay, so from here, let's see, we remember that k equals all the numbers, 0, 1, 2, all the way to n minus 1. What is n minus 1? Well, n is 3, so that'd be 3 minus 1. So n minus 1 is 3 minus 1, which is 2. And because it's 2, that means we're just going to we just go up to 2. So we go from 0, 1 to 2. And so we stop at 2. Great. So the first 3 numbers. All right, so now we can just plug in the different k values and get 3 different answers and be done. And again, this one, for some reason, the values it's looking for is not a fully worked out problem. It just wants you to find out what it looks like in its format. Here's what I'm saying. We just need to figure out cosine of these values and these values, and we just need to write down this expression as fully. We don't have to like multiply cube root of 15 into it, we can just keep it in trigonometric form, our answer. Maybe that was more confusing than it needed to be. Don't worry about it if it was confusing, because you'll find that soon, or if you don't already know. Okay, so I'm going to try to write a shorthand for this so that it's kind of simpler. So everything else is going to be the same. All this is the same. And all that is the same. Okay, so this is negative 0.927 plus 2 pi times 0 over 3. And this is negative 0.927 plus 2 pi times 0 over 3. This is negative 0.927 plus 2 pi times 1 over 3. This is negative 0. It's just kind of methodical. 7 plus 2 pi times 1 over 3. You can fill a chalkboard with this. Negative 0.927 plus 2 pi times 2 over 3. Negative 0.927 plus 2 pi times 2 over 3. Great. Okay, so from here, we can just pull out a calculator and solve each of these. Or see each of these values and get a raw number for each of these values. So we can plug them in. Okay, so this becomes, we can just, here's what I can do. I will plug in 0, I'll store 0 for k. And then I'm going to run this value literally in the calculator. So I'll do negative 0.927. Actually, I'll clear that. I'll put in parentheses first, negative 0.927 and so on, plus 2 pi and times, times k. And I'm doing this now so I don't have to type it over and over again. I'll just put in once, and then I can just change k and get different values. So that gives me negative 0.309. So that's negative 0.309. I want to write that down real quick. So that becomes, let's see if I can, is there an easy way to write this? It's not confusing. I think I'll write negative is, yeah, let's do this. So let's do this. So this is problem number 1. This is problem number 2. This is problem number 3. And then I'll make this same thing over here. Problem number 1, problem number 2, and problem number 3. Okay. So problem number 1, we have negative 0.309 and so on. But here's the thing. We don't like negative values. We want to have a positive value as our answer. So we need to find a coterminal angle that'll count for this. So we need to find a coterminal angle that we can plug in that'll represent negative 0.309. So to find the coterminal angle, we can just add 2 pi. That gives us 5.974. Yes, so we get 5.974. So we'll actually put instead, we'll put 5.974. And over here, next to it, we'll do the same problem again, except, actually before we do that, now we're going to do the second problem. After I write this over here as well, 5.974. And then down here, I'm going to write, I want to make k1, so 1 stores as k. This isn't so confusing. And I'll run the same thing. And I get 1.785. Okay, so I'll put 1.785 and 1.785 for there. And then finally, I'll do the same run again, and I'll plug in 2 for k. 2 is not going to be k. I'll run the same equation again. That gives me 3.879. This is 3.879 and 3.879. Okay. And all right. Yeah, okay, we can do that. This works. And then from here, we can write the rest. Now we need to write that cube root of 15. That cube root of 15 is, let's actually calculate that. To find the cube root, there's a bunch of ways to do it. Here's one way. I can hit math, and I can just hit the cube root, that's number 4, and I'll put in 15. And that gives me 2.466. So I'll put in 2.466. And we will do 2.4. Actually, let's make sure that I'm lining this up. So 2.466, yes, 2.466 times the cosine of all that, 2.466 times the cosine, and 2.466 times the cosine of all that, and we're going to add plus I times the sine, plus I times the sine, plus I times the sine. And then we're going to add that last parentheses. And those are our answers. Now, here's the thing. It says the cube root with the smallest positive argument is the thing I want you to put in the first. And so you see the smallest positive argument is actually this, the number 2. Number 2 has the smallest positive argument. That's the smallest angle. And so we're going to plug in that one first when you plug it in to the answer box. So if you wanted to reorder it, it's probably better to start with the smallest one. So this one actually goes first. And then after that, you'd put the third one. So the third one would go next. And finally, the first one would go last in the answer box. So that's kind of the ordering you want to put it in, because it asks for you to put it in the order of the size of the argument. So I'm going to go ahead and I can just move this up here and reorder, reset that. There we go. So there you go. And those would be your answers for 14. Great. Now there's a bunch of, oh, it looks like I lost the parentheses there. Whoop. Now there's a bunch of other problems, 15, 16, and 17, that all ask you to do the same thing. And I actually cut those out because of the homework, because they just seemed really redundant. You're doing the same thing over and over and over again. And it's not to say it's a bad thing to be doing the same thing over and over and over again, but you've done enough of that already. So I think for now, considering the state we're in and what we're doing, I think it's better if we just move on instead of giving you more suffering. So I'm going to skip over to the last problem, which is probably, what is that? Probably 15 in your homework, but it's 18 in mine. So let's do this one. I know we're running out of time, but we're in the last problem. We finished the timer, but we just made it to the end problem. I think this won't take too long, so we're just gonna quickly finish this up and we'll be done. So we have find the 4th roots of unity and express them in terms of a plus bi. Okay, so a plus, we need to find those 4th roots of unity. Now remember, you may remember from the lesson itself exactly how to find the 4th roots of unity. To find the root of unity, we find the cosine of 2 pi k over n plus I times sine of 2 pi k over n. So we'll go ahead and plug those in. Okay, cosine 2 pi k over n. Let's see. So let's see. The nth root of 1 equals the cosine of 2 pi k over n plus I times the sine of 2 pi k over n. And then k equals, 0, 1, 2, all the way up to n. And so it looks, n minus 1, excuse me. And so n minus 1, or n, in this case is 4. So if you do n minus 1, we're going all the way up to 3. So the first 4 numbers are 0, 1, 2, and 3. And 3 in our case. So we will do just plug them in. So we get the cosine of 2 pi, let's do 2 pi 0 over 4 plus I times the sine of 2 pi 0 over 4. And then I'll just kind of copy this down. 3, 4, okay. I want to make this line. That's a bit sloppy. Let's align this here. Okay, so we get 2 pi 0 over 4. This would be 2 pi over 4. This would be 4 pi over 4. And then finally this would be 6 pi over 4. 2 pi over 4, 4 pi over 4, 6 pi over 4. Great. So I times the sine. And you get the idea. You know what the rest of this is. So I'm not going to copy it all over just to waste your time. So 2 pi over 4, that's the same thing as pi over 2. 2/4 pi over 2. And so cosine is 0. Sine is 1. So this would become, actually, let's start with the 0. 2 pi 0 over 4, this is just, oops, let's not use an eraser instead of a pen. This becomes 0. This becomes, this is also 0. And so the cosine of 0 is 1, and the sine of 0 is 0. So what we get with this, let's use, I don't know, let's use blue. What we get is 1 plus I times 0, which is 1. Unsurprisingly, we always get 1 at some point or another. Let's do the next one. 2 pi over 4. That is 1/2 pi. That's pi over 2. Pi over 2. And the cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we'll do, this becomes 0 plus 1i, or just I. Okay, 4 pi over 4, you kind of get the rhythm here. This is just pi, and this is just pi. Pi is -1, 0, so we get, that equals -1 plus 0i. 0i is just 0, so that's just -1. And finally, we get 6 pi over 4. We finally get 6 pi over 4. 6 pi over 4, that is the same as 3/2 pi. 3/2 pi. So this is 3 pi over 2, 3 pi over 2. Okay, and that becomes, let's see, that's 0, and so this, yeah, that becomes 0, and then plus, let's see, it'd be a -1 for I, so, or yeah, -1 for y, or -1 times I, which is just -I. And that is our answer. So our 4 answers then, our 4 answers for this one is just 1, I, -1, and -I. And that looks like D. So that'll be our answer. And we're done. And we're done with our homework. Thanks for working through all that. I hope you learned a thing or two. I hope you found it a little bit enjoyable. I think the roots of unity are some of the coolest things in math now. I'm just so stoked about the roots of unity, and I think you should like them too. But I hope you found it at least bearable. I'll see you in the, I'll see you in the next video.